So let's look at the next one. Variable resistors in a potential divider circuit. Variable resistors in a potential divider circuit. If one of the resistor in a potential divider circuit is a variable resistor, how will you handle it? So let us say you have this resistor R1, which is a variable resistor here, and you have resistor R2, which is a fixed resistor, and are connected to a battery of EMF E, having a negligible internal resistance. This means that the PD across the variable resistor will be changing, as the resistance of the variable resistor is what is changing. But the PD across the fixed resistor will then complement the PD across the variable resistor to still produce a constant EMF of the battery. Is that okay now? Because the EMF of the battery is what? Is constant. So if a variable resistor is in a potential divider circuit, as the resistance of the variable resistor changes, the PD across the variable resistor will be what? Will be changing. But the PD across the fixed resistor will complement the PD across the variable resistor in order to still produce a constant EMF because the EMF of the battery, the EMF of the circuit is still what? Is still constant. What do I mean by complementary it? It simply means that the PD across this plus the PD across it will always produce the same EMF of the what? Of the circuit. Therefore, if the PD across R1 increases, the PD across R2 will reduce in order to still produce the same, because the EMF of the battery is still what? Is still constant. So for example, let us say we connect a voltmeter across this particular variable resistor R1, and that voltmeter is having a negligible, that voltmeter is having an infinite internal resistance. Voltmeter with infinite internal resistance, they are referred to as ideal voltmeter. So, and the question is this. So note that if R1 increases, then PD across R1 increases. Therefore, PD across R2 will reduce. In this case, the voltmeter reading increases. The voltmeter reading connected across R1 increases. According to this equation, the voltage across R1 here is given as R1 over R1 plus what? R2 times what? Times E. So we can see that the voltage across R1 is proportional to the resistance of R1. So if the resistance of R1 increases, the voltmeter reading across R1 will increase. Therefore, the PD across R2 will reduce because the EMF of the circuit is still what? Is still constant. How about if I have a situation like this? Let us say that we have this case. This is the variable resistor R1, this R2, and we want to find the voltmeter reading. The voltmeter reading across what? R2. The same thing applies here. If R1 increases, if the reading of the variable resistance increases, then the PD across R1 will increase according to this equation. Therefore, the PD across R2, which is the fixed resistor, will reduce because the EMF of the battery is still what? Is still constant. Otherwise, I can do it like this. V2 will be given as R2 over R1 plus what? R2 times what? Times E. Don't forget that the variable resistor there is not R2, it is what? It is R1. The variable resistor there is not R2, it is what? R1. And in this case here, you can see that the voltmeter reading across R2 is inversely proportional to the reading of what? R1. So if the resistance of R1 increases, the voltmeter reading across R2 will reduce, because the variable value there, which is the value of the variable resistor, is inversely proportional to the PD across R2. But in this case, the voltmeter reading, which is the PD across R1, is directly proportional to the reading of the resistance of what? To the value of the resistance of R1. So whether you are using this expression to explain it, or you are using the proportionality, provided you understand that the variable, your independent variable, is the resistance of the variable resistor, and sometimes it can be contributed directly to it. That is, if you are looking at the voltmeter reading across the variable resistor, the voltmeter reading will be directly proportional to the resistance of the variable resistor. But if the voltmeter is not connected across the variable resistor, then the voltmeter reading will be inversely proportional to the resistance of the variable resistor. Another way to look at it is this. Another way to look at it is this. If I want to explain it like this, I could have said the voltmeter reading across R1. Look at it here. The voltmeter reading across R1 is given as IR1. And the variable resistor there is what? Is R1. Therefore, the voltmeter reading is proportional to the resistance of R1. So if the resistance of R1 increases, the voltmeter reading will do what? Will increase. Is that okay? Now, if I want to explain this, the voltmeter reading across R2 is given as IR2. R2 here is a fixed resistor. So if I want to explain the voltmeter reading, I'm going to explain it in terms of the current, not in terms of resistance, as in this case. So what do I do? If the resistance of R1 increases, the combined resistance of the circuit will increase. If R1 increases, the combined resistance of the circuit increases. And if the combined resistance of the circuit increases, remember we said that the current is given as E over what? R1 plus what? R2. If this combined resistance increases, then the current supplied by this battery will reduce. Therefore, the voltmeter reading across R2 will do what? Will reduce. What I've explained is that simple. If R2 is a fixed resistance, you have to look at how the value of the resistance of the variable resistor is affecting the current supplied by the battery. If the resistance of the variable resistor is increasing, then the current supplied by the battery will reduce. Therefore, the voltmeter reading across R2, because it's not dependent on current primarily, the voltmeter reading across R2 will do what? Will reduce. So you can either explain it this way or using this expression. I can either be using the equation of the potential divider, or I'm using this word, this expression.